Hello everybody. So in this lecture we're going to go over the finite potential well, which is qualitatively very similar to the infinite potential well in terms of how the solutions appear and how they look like and how they respond to the modulation of the well widths, for example. However, the process of actually determining the exact wave functions or the exact solutions to this problem is certainly different. And it's different in the sense that we actually have to break apart this problem into three. The three parts being this left side of the well. So we can call this like the left well or left side. And then we can call this the well, and then the right side of the well, if you will. We break these apart into regions 1, 2, and 3, respectively. And so the total wave function, if you will be broken apart into three parts like this, right? Where this is only true for x is minus, or x is less than Lx over 2, and this is true for anything in between Lx over 2 and Lx, or minus Lx over 2 and Lx over 2. And the third region is true for positive Lx over 2. All right. I've chosen this convention just because it simplifies things a bit. I could have done 0 to Lx. It wouldn't have made any difference, but this makes things a bit simpler for me. And so we have this finite potential. All right. And we recall that the Schrodinger equation is as follows. I'm just rewriting the Schrodinger equations for the unidimensional form. It's an eigenvalue problem. And the solutions to this are written as follows. I've written it 3 different times. I've written it once here, and once here. And I think I've already went over the 2 different solutions for the case of a problem of constant potential. There's 2 solutions for this sort of free particle, for the free electron solutions, and they can be written as in their exponential form, essentially. So a constant, in this case c, times exponential of ikx plus a constant of, in this case g, times the exponential of minus ikx, right? This allows me to write any sort of wave function here. And this is, of course, this is just true for any case when v is not changing, when it's constant, which is true for this first region, for all of minus, or all of x less than negative Lx over 2. But likewise, I can say this for region 2, and I can say this for region 3. All right? And so what this allows me to do is it allows me to define some constants, some wave vectors k, which would be equal to 2m times e minus v over h bar squared. And in the case of this first region, I am saying that v is equal to v naught. So I can rewrite this as 2m e minus v naught over h bar squared. All right. And of course, in the second region, I'm calling v as 0. It's just the well, essentially, and there is no potential in this well. So I'm just going to call this as 2me over h bar, and this is simply going to be equal to k1 over here, right? Because we have a potential of equal heights both in the left side and the right side of the well. Okay? And so we can simplify this down. And the reason why we can simplify this down is as follows. So we recognize that k1 is simply equal to k3. And we can see here that if we switch around the order of the subtraction, so all I did here was I switched around e and v naught, and I'm multiplying. I added a factor of -1, which allows me to write this as I times 2m v naught minus e over h bar squared. And this is just equal to nothing other than what I'm going to call I times kappa. I'm writing kappa as this, where this square root term is my kappa. All right? And so if I substitute this in for I times kappa into K1 and K3, which I can do down here, I have I times kappa everywhere, right? Right? And this can be rewritten or, expanded as C exponential. I'm just multiplying my i's out this time, minus kappa x plus G exponential plus kappa x. And this is F exponential minus kappa x plus H exponential plus kappa x. All right. Now, intuitively, what do we see here? Well, we can see here that, and this is true for every eigenstate, by the way. I drew here just my finite potential well, and this is simply it's the first state. And you can see here, it's a rough drawing, but you can see here at the left side of the well, it is increasing exponentially. I have an increasing exponential of my wave function. And on the right-hand side of the well, I have a decaying exponential of my wave function. So what this tells me is that for the first part of the well, or for the first region, this G, or the C, this amplitude has to be equal to 0. And for the third region, this amplitude here must be equal to 0. And the reason for this is because as x is increasing, recall that positive x is in this direction, for this first portion of the well, right, for the first region of the well, I only have an increasing exponential. And for the third region, I only have a decaying exponential. This is true. And in order for the only way that this can possibly be true is if these amplitudes are 0. All right, and so that said, I can rewrite this as G exponential of kappa x, and this is F exponential minus kappa x. All right, so this is my solution of the first region and solution to the third region. All right. Okay. So now we get into our boundary conditions. And so our the reason this is necessary is essentially to find our particular solutions, of course, right? And so boundary conditions, going back to differential equations, in order to find any solution to a differential equation, you need some sort of constraints to your system, and these are our constraints. The first constraint is that is continuity of the wave function. So we're not presuming, or this doesn't even make any sense, having a wave function that breaks apart in any way, such that you have some weird wave function where you have this guy going on. This just is weird. I don't know what to say other than it's unphysical, and it's unphysical, and no such solution. You can't devise a problem in which that would be the possible solution, and so certainly not for an eigenstate. And so so we're presuming continuity of psi, and continuity of psi means that regions 1 and 2 are equal to one another at this boundary. All right, at minus Lx over 2. So we can so I've written down the solution to the left-hand side to psi 1, right, over here, and this is equal to psi 2. And I simply have to fill in the point at which that is true. And likewise, for regions 2 and 3, I'm going to fill in the point for which that is true. Lx over 2, Lx over 2. All right, that's this guy here. Now, we note two trigonometric identities. Sine of minus x is simply equal to minus sine of x. And another trig identity is a cosine of minus x is equal to cosine of x. And so that, keeping that in mind, we can rewrite this as minus a sine of KLX over 2 plus b cosine of KLX over 2. All right. Now we have another constraint, another boundary condition. And in this case, it's for our derivative, d psi dx. Right? And now this is important because, otherwise, if we only had this particular boundary condition, you can devise particular solutions where, you'd have some sort of kink of some sort, discontinuities in derivatives manifest as kinks in the integral of those functions. So that's not a physical particular solution for these eigenstates. And so we're going to affirm that this is our second boundary condition. And if you take the derivative of g exponential kappa minus Lx over 2, you essentially you pull out your kappa out up front, and it actually turns out that in this case we have negatives across all of these elements here in our summation, and in the front of this exponential, and all of the negatives cancel out. And so you can work through these derivatives. I essentially just took the derivatives of both sides of the equation, and I set them equal to one another at these exact same points. One thing I forgot to point out is that you see this k here. I've already defined what kappa was, which was 2m v naught minus e over h bar squared. K is simply our wave vector of the well, which is 2me over h bar squared. So I just wanted to point that out in case you guys haven't caught that on. So I set k2 equal to k essentially, right? So in any case, now what we can do is we can simplify terms here, and we can do that by adding this first term and this third term. All right, so the first and the third, I've denoted them here. Actually, I have 1, 2, 3, and 4. And if I add 1 and 2, I get 2b cosine k Lx over 2 is equal to quantity f plus g times the exponential of minus kappa Lx over 2. All right, and so that's what you get when you add these two terms together. Right, you get this f plus g, and then this is the same, and our sines cancel out here, and you're only left with these cosines, and so you have this 2b out up front. All right, so you do that, and you can do the exact same thing for equations 4 and 5, and you can end up with these expressions here. And if you divide these together, what do you get? So if I divide this first equation up here, if I divide this, or if I divide the other way around actually, if I divide this equation here by this equation up here, divide. And this can only be true if f is not equal to g, of course, because if f were equal to g, such a division wouldn't make sense. You'd be dividing by 0. You have a tangent, so you can bring this over here. You have a tangent of KLX over 2 is equal to kappa over k. All right? And if you do the same thing, if it's something similar, but instead of adding and subtracting, you subtract and add respectively, you end up with these two expressions, these two equations. All right, so instead of an f plus g, over here you have an f minus g, and rather than canceling out your sines, you cancel out your cosines, and you're only left with sines. And once again, if you divide, this time presuming f is not equal to minus g for the same reason that we can't let f equal to g up here, what we have is a minus cotangent of k Lx over 2. Recall a cotangent is simply a cosine over sine. So I'm taking this equation and I'm dividing it by this entire expression over here, right? So I'm left with this kappa over k over here, and I have this cotangent of this cosine over sine. Okay, and of course the two a's and the two b's here just cancel out. All right, so we have these two expressions, and this actually brings us to our particular solution, believe it or not. This may not seem obvious at first, but it is obvious because we have a transcendental equation. It's a transcendental equation, and what transcendental equations tell us, what these means, transcendental equation, what this means is that there are only particular values of E that make this equation true, because we recall that K is equal to, or K is proportional to the square root of E, right? And kappa is proportional to the square root of E minus, or the other way around, V naught minus E. Okay? And so with this proportionality, which values of E, and this is the question, right? Which values of E make this relationship true? And you can solve this, this is pretty straightforward if you plot this out. So if we take this left-hand side of the equation, tangent of k Lx over 2, and we plot this out for all of E, we get these functions. So you have this blue line here, you have another blue line here, and this other blue line here, okay? And this is the function that kind of you can expand this to make this obvious. And so you essentially plug this into something like Mathematica or MATLAB, and what you get is this a function that looks very similar to this. I try to draw it roughly, but it's not exact. Likewise, you can do this for minus cotangent of this argument here, and you get the yellow lines. So I try to color code them here. And of course, then what you can do is you can take this kappa, right, and k, right, which is just the ratios between the two. And what you get is this value here, the square root of E minus V naught over E. And that is, of course, a decaying or a 1 over x function, right? And wherever you have an intersection is where the expression here on the left is true. One of these two expressions are true wherever you have an intersection. And these intersections are our energy eigenfunctions, right? Because we're essentially scanning through all values of E, all the infinite values of E, and we're finding which points along this, all real numbers of E, essentially, make this transcendental equation true. And in this instance, what I did here is, this is one example. I took a case where V naught was equal to 25 electron volts and a well width of 0.5 nanometers. All right, and so if we have this system here, this is a finite potential, of course. These are the energy eigenvalues over here. Okay, so all I essentially did was I went onto MATLAB and I plugged, or I made a function, an array of E, and I substituted V naught into this expression, and I plotted these functions. And by plotting these functions, I found my energy eigenvalues. And there are only 5 in this case. You will notice that there comes a point where there are no more constrained or discrete states. It actually turns out, and we're going to talk more about this later, that the possible energy eigenvalues above this potential well are continuous. You have continuous eigenvalues up here. Okay. But within this potential well, they are discrete, as you can see here. And so these are our solutions, or our energy eigenvalues, for the case of a potential of height 25 eV and a well width of 0.5 nanometers. And you can substitute these values into this these functions here in order to find those energy eigenstates. And the eigenstates will look very similar to the case of an infinite potential well. They'll look something like this. Then you'll have something like this. Then you'll have something like this, and so on and so forth, okay? But the only difference, and you'll note this, the big difference, I should say, it's not just some trivial thing, is that you, for the first time, can see that there is actual penetration within the wells. So there is a possibility of actually finding the electron within the well. It was the case of the infinite potential well where this simply was not true. So for the infinite potential well, we had a boundary where at this x equals 0 and x is equal to Lx, the wave function was equal to 0. This was a boundary that we set for ourselves. All right, and so this finite potential allows some penetration of that wave function and thus a probability density within the well. And so there's a non-zero chance that you can actually find the electron inside the barriers. And that's highly quantum mechanical. So I hope this was helpful, and we're going to go over a problem related to this later. And so, yeah, let me know if you have any questions, and I'll see you guys in this next video.